Good morning, everyone. Hope you are all doing fine. Today we're going to deal with the second part of aldehydes and ketones. Last video we dealt with the structure of aldehydes and ketones and how they differ from each other, their nomenclature, whether common nomenclature or EUPAC. The common nomenclature of aldehydes was based on the name of the acid that the aldehyde comes from, and then we removed the IC and we added the word aldehyde. The EUPAC nomenclature came from the alkane that contains the aldehydic group. We removed the E and we added an al in its place. The common names of ketones was either something like acetone and acetophenone, just common names of no specific reason related to the structure, or we could name the different alkyl groups attached to the carbonyl. So something like this example, it would be an ethyl methyl ketone. Their EUPAC nomenclature was based on the structure, on the name of the alkane that has the same number of carbons, and then we removed the E and we added an on at the end of the name. Then we dealt with the synthesis of these compounds, and we said that they can be synthesized by four main different methods. The first was oxidation. The second method was from geminal dihalides. The third method was from alkynes through hydration, whether Markovnikov or anti-Markovnikov addition of a molecule of water. And finally, they could be prepared from acid derivatives, whether by reduction or by using organometallic compounds. The oxidation, we agreed on that primary alcohol gives aldehydes, but we have to use a specific oxidizing agent like PCC, otherwise they will continue to give the acid. In case of secondary alcohols, their oxidation gave ketones, and we had another selective method for the oxidation of secondary alcohol giving ketones, which was the Oppenauer oxidation reaction. From alkynes, we just hydrated an alkyne giving aldehyde if we use an anti-Markovnikov conditions, or it would give a ketone if we use the Markovnikov hydration. From geminal dihalides, the reaction only relied on using a nucleophile, which is the OH, and removing two geminal dihalides and putting the OHs in their places. This is a geminal diol, which is unstable. It loses a molecule of water and it gives the aldehyde or the ketone. Finally, we could prepare them from acid derivatives like acid halides and esters, either by the selective reduction. In case of acid halides, we reduced using the Rosenmund reduction, which is hydrogen, palladium, barium sulfate, sulfur, and quinoline, ending into the aldehyde, or we can use Grignard and stop at the ketonic compound. However, as we mentioned, this reaction is not selective and it might not stop at the ketone or the aldehyde produced, and it might proceed to give the tertiary alcohol, and it's better to use something like dialkyl cadmium, which is only selective to acid halides and will not react with the produced ketone. Afterwards, we dealt with the reactions of esters to give aldehydes and ketones, where we could again reduce the ester using the dibal at negative 80 degrees centigrade to give an aldehyde, or we can again use Grignard to give the ketonic or aldehydic compound, which is, as we said, non-selective and not a preferable method. And then we had a specific type of methods of synthesis for only for aromatic aldehydes and ketones, which was the Friedel-Crafts acylation, giving aromatic carbonyl compounds. And then we dealt with the physical characters of these compounds, and we said that they are incapable of forming hydrogen bond on their own. However, they can accept a hydrogen bond from water. Today's lecture will deal with the reactions of aldehydes and ketones. Reactions of aldehydes and ketones are four types. The first type is nucleophilic addition reactions. As we have mentioned in the previous video, in part 1 of aldehydes and ketones, the carbonyl group has a carbon that is carrying a partial positive charge. Accordingly, it can be attacked by different nucleophiles, breaking the double bond between the carbon and the oxygen. So the first type of reaction is the nucleophilic addition reactions, and we shall deal with it in full details. The second type of reaction is a condensation reaction. The condensation reaction involves first a nucleophilic addition followed by a loss of molecule of water. It's exactly the same as we have just drawn. However, after the reaction proceeds and we have an OH on the carbon of the carbonyl and we have a hydrogen on the nucleophile, we lose a molecule of water and we form a double bond between the nucleophile and the carbon. It's as if you have removed the oxygen and you have added the nucleophile in its place. This is the second type of reactions of aldehydes and ketones, and this is where we will stop in this video. The third and the fourth types will be discussed in the next video, which is part 3 of aldehydes and ketones. They deal with the third type is reactions related to the alpha acidic hydrogen. In case of aldehydes and ketones, if the carbon alpha to the carbonyl is carrying a hydrogen, this hydrogen is acidic. Why is that? Because if we remove it by a base, it will leave a negative charge on the carbon, and this negative charge is stabilized by resonance. And accordingly, the hydrogen is easily removed as a proton, and this is the exact definition of an acid. An acid is a compound that can release a proton. These compounds, if they have a hydrogen directly attached to the carbon, which is alpha to the carbonyl, this hydrogen is acidic and it can be easily removed using bases. These are three types of reactions that will be discussed in full details next video. The fourth type of reaction is the oxidation reduction reactions. As we have mentioned before, aldehydes is a step between alcohols and acids. If you oxidize alcohols, you reach aldehydes, and if you further oxidize, you will reach acids. However, if you reduce acids, you will reach aldehydes, and if you further reduce them, you will go back to the alcohol. So they are a step in between the acids and alcohols. They are in the middle of mutual oxidation reduction reactions. Okay, so this is the fourth type of reactions. Let's first deal with the nucleophilic substitution reactions. So the first type is the not nucleophilic substitution, it's a nucleophilic addition reaction. So the first type is the nucleophilic addition reactions. In this reaction, we have a carbonyl that is carrying a partial positive charge on its carbon, and we have a nucleophile that is either carrying a lone pair of electrons or a negative charge. And it will attack the carbonyl, breaking the double bond, giving the OH and the nucleophile both attached to the carbon of the carbonyl. What I have just drawn is the reaction mechanism of a strong nucleophile. In case of strong nucleophiles, and these are compounds that are carrying a full negative charge, you will have a direct attack immediately from the nucleophile to the carbonyl carbon, which is carrying a partial positive charge. However, if you actually have a weak nucleophile, this will not be the case. Why is that? Because your nucleophile is only carrying a partial negative charge or a lone pair of electrons. So it does not have a full negative charge. So it's incapable of attacking a carbon that is only carrying a partial positive charge. It needs a carbon that is carrying a full positive charge. So to facilitate such a reaction, we add a drop of an inorganic acid. You have to see in the reaction conditions an inorganic acid. You have to see a proton. What is the role of this proton? It protonates the oxygen of the carbonyl. So now the oxygen is carrying a positive charge, since it has been protonated by the proton of the inorganic acid. Accordingly, the oxygen, due to the fact that it's more electronegative than the carbon, it will attract the electrons of the bond, breaking the pi bond between the carbon and the oxygen and giving the full positive charge to the carbon. Now a weak nucleophile can attack this carbon, giving the same product, which is a carbon attached to the OH and the nucleophile. So in both cases you have the same steps. The only difference is in the arrangement or the sequence of these steps. In both cases you have to break the pi bond between the carbon and the oxygen. You have to attack the carbon by a nucleophile, and then you protonate the oxygen that is now carrying a negative charge. The sequence or the order of reaction depends on whether the nucleophile is a strong nucleophile or a weak nucleophile. As I have mentioned, strong nucleophiles are compounds that actually carries a full negative charge. Weak nucleophiles are compounds that are carrying a lone pair of electrons or a partial negative charge. Again, if you feel confused, do not use the weak nucleophile mechanism except if you see a proton in your conditions. If we add conc sulfuric, or if we add dilute HCl, dilute sulfuric or conc sulfuric or dilute HCl, any inorganic acid. If you see inorganic acid or a proton drawn on your arrow of the reaction, then we actually need you to use the weak nucleophile mechanism. However, if the proton does not exist, you have to use the strong nucleophile mechanism. As we have mentioned, you have group of steps. First, one of them is breaking the pi bond between the carbon and the oxygen. Another step is the attack of your nucleophile. A third step is the oxygen takes a proton from the medium. In case of strong nucleophile, the attack comes first and then the double bond breaks and the oxygen takes the proton. In case of weak nucleophile, the oxygen will take the proton first, then the nucleophile will, first the oxygen will take the proton from the medium, and then the double bond will break, and finally the nucleophile will attack the carbon that is carrying the positive charge, now the fully positive charge. So this is how the mechanism proceeds, whether it's a strong or a weak nucleophile mechanism. We have difference in reactivity between aldehydes and ketones. If you think of it, you will have to notice that the whole reaction depends on the presence of a positive or a partial positive charge on the carbonyl carbon. The more the positivity of this carbon, the better the reactivity of this compound, since you are attacking using a nucleophile. So the more the positive, the better the reaction. In case of aldehydes, you have only one R as an electron donating group, giving electrons to the carbonyl, reducing its positive charge. However, in case of ketones, you have two electron donating groups giving electrons to the carbon. So definitely the carbon of the aldehyde is having a more positive carbon than the carbon of the ketone, and accordingly it's more reactive. So aldehydes are more reactive than ketones. The second reason for the same property, which is that aldehydes are more reactive than ketones, is the steric effect. In case of both reactions, you are attacking using a nucleophile, so you have an sp2 carbon that you're going to be converting into an sp3 carbon. As we all know, sp3 carbons are crowded carbons. Because they are tetrahedral, the angles between the bonds is much lower than in case of sp2 carbons. The angles here are 109, while the angles here are 120. So this is less stable than the linear compound. The tetrahedral compound is less stable than the linear compound. Accordingly, if you add something that increases the static hindrance, which is another R, in case of aldehydes, one of these R's is an H. So this is reducing the static hindrance. We only have the R, one R, and a nucleophile and an OH. The H does not count in static hindrance. However, in case of ketones, you have an R and a second R. So this is producing some sort of a static hindrance, which is again reducing the reactivity of ketones and making aldehydes more reactive towards these reactions. Furthermore, if we compare aliphatic with aromatic aldehydes and ketones, we will find that aliphatic compounds are more reactive than aromatic compounds. Why is that? Because in case of aromatic compounds, you have the carbonyl group directly attached to a benzene ring. So you have the carbonyl attached to a benzene ring, regardless what you have on the other side of the carbonyl. A benzene is not an electron donating nor an electron withdrawing group. It depends on whatever is attached to it. If it has a group that withdraws electrons, it will give electrons. If it has a group that donates electrons to the ring, it will accept the electrons from whatever is donating. So it depends on what is attached to it. According to what is attached to it, whether it's donating or withdrawing, the benzene will do the other rule. If I attach an electron withdrawing group to the benzene ring, then the benzene ring will act as an electron donating group. If I attach an electron donating group to the benzene ring, then the benzene will act as an electron withdrawing group. In case of carbonyls, carbonyls are electron withdrawing groups. So accordingly, the benzene will donate electrons to the carbonyl. And accordingly, the positive charge on this carbonyl is very low. So aromatic compounds are much less reactive than aliphatic compounds. If you add on the side chain attached to the carbonyl an electron, whether this side chain is aliphatic or aromatic, an electron donating group, then you're giving electrons. So you are reducing the positive charge. Accordingly, you are reducing the reactivity. However, if you attach an electron withdrawing group, it attracts electrons towards it, away from the carbonyl. So it increases the positive charge on the carbonyl. So accordingly, it increases the reactivity of these compounds. Let's look at the slides that discusses these points. As we have mentioned, reactions of aldehydes and ketones are 4 types of reactions, either nucleophilic addition or condensation, where we first perform nucleophilic addition followed by elimination of a molecule of water, reactions due to the alpha acidic hydrogen, and the oxidation reduction reactions. As we have mentioned, the first type of reactions of aldehydes and ketones that we're going to discuss in full details is the nucleophilic addition to the carbonyl group. And we said that the carbon of the carbonyl is carrying a partial positive charge, which will be attacked by the nucleophile, and you end up with a carbon carrying the nucleophile and the OH in addition to whatever was attached to the carbonyl at the beginning. We said that we have 2 mechanisms, a strong nucleophile mechanism and a weak nucleophile mechanism. In case of the strong nucleophile mechanism, the attack of the nucleophile, then breaking of the double bond and attachment of a hydrogen to the oxygen. In the weak nucleophile mechanism, the hydrogen attaches first to the oxygen through protonation, followed by breaking of the double bond and then attack of the nucleophile. So we have 3 steps. It depends on whether the nucleophile is a strong nucleophile or a weak nucleophile. We will arrange them. The steps are: a bond is broken, a nucleophile is attacking, and a hydrogen attaches to the oxygen. It depends on whether your nucleophile is weak or strong. You will arrange them. In case of strong nucleophile, the attack comes first, the double bond breaks, and then the hydrogen attaches. In case of the weak nucleophile, the hydrogen attaches first, and then the double bond breaks, and then finally the nucleophile will attack the fully positive charged carbon. Then we discussed the order of reactivity of aldehydes and ketones, and we said that aldehydes are more reactive than ketones due to two factors, which are the electronic factor because of the donation of only one side chain, while in case of ketones, two side chains are donating electrons, and we have the steric factor because in case of aldehydes, one of the groups attached to the carbonyl is a hydrogen, and thus this compound will not be reluctant, will be less reluctant to conversion into the sp3 carbon. As we have mentioned, if you add electron donating groups to the side chain, this reduces their reactivity, while if you add electron withdrawing groups to the side chain, this improves the reactivity of these compounds. And again, as we have mentioned, if you discuss the order of reactivity of aromatic carbonyl compounds versus the aliphatic carbonyl compounds, we will find that the aliphatic are more reactive because of the electron donation power of the benzene ring. And again, if you add an electron withdrawing group to the benzene, you are reducing the reactivity. And if you add an electron if you add an electron donating group, you are reducing the reactivity. And if you add an electron withdrawing group, you are improving the reactivity. Now we will discuss three different types of reactions that are considered, that are regarded as examples of nucleophilic addition reactions to the carbonyl compounds. The first type of reaction, or the first example of reaction, is the addition of alcohol to aldehydes and ketones. If you have a carbonyl group and you have an alcohol, the alcohol has a lone pair of electrons and the carbonyl is carrying a partial positive charge. As we have mentioned, alcohol here is regarded as a weak nucleophile, so you have to add an inorganic acid so that you will proceed using the weak nucleophile mechanism. You break the double bond, you have the COH and then a positive charge on the carbon, which will be attacked by the lone pair of electrons on the alcohol, giving a carbon which is attached to an OH and an OR, no matter what else is attached to the carbonyl. If you see this structure, which is a carbon attached to an OH and an OR, this is regarded as a hemiacetal compound. If it was an aldehyde, then this is the hemiacetal. If it was a ketone, then this is the hemiketal. However, hemiacetals and hemiketals are very unstable compounds and they spontaneously lose a molecule of water, giving the aldehydes and ketones once again. If we need to stabilize these compounds, we convert them into the full acetal and the full ketal. And what is a full acetal or a full ketal? These are the aldehydes or ketones where you add the alcohol molecule. So you have an OH and an OR, and then you add another molecule of alcohol, giving two O-alkyl groups attached to the carbon. These are the full acetals or the full ketals, and these are more stable than the hemi compounds. And we can actually use these compounds to protect. They are used as protecting groups for aldehydes and ketones if we need to perform a reaction on a side chain and we fear the interference of the aldehyde and ketone. One very good example, very famous example of these protecting groups are the ethylene glycol. You start the reaction having an aldehyde. If you have such a compound, a ketonic compound that has an it has a double bond in its side chain, and you actually need to prepare this compound from your starting material. What you need here to do is to add potassium permanganate to the alkene so that you would introduce a diol, a vicinal diol. However, if you use potassium permanganate and this is an aldehyde, you will end up oxidizing it into the acid. If this is not what you need and you need it to stay as an aldehyde, you will need to protect it first. How do we do that? Using something like ethylene glycol, producing the cyclic acetal. In this case, you have the C attached to the doubly bonded compound, and then you have the double bond O will be broken into two oxygens attached to the two carbons of ethylene glycol. This is this carbon, and this one is that carbon, and then you have the O and the O. This is your this is your cyclic acetal compound. Then you perform the potassium permanganate reaction to produce the diol compound. And then you hydrolyze your diol compound to give your final product. However, these conditions for protection, if you use cyclic acetals for protection, you have to make sure that your reaction will not proceed in acid conditions. Why is that? Because your acid conditions will hydrolyze the cyclic acetal and the cyclic ethyl. So this reaction has to be performed in alkaline or neutral medium. Otherwise, you cannot use cyclic ketals or cyclic acetals for the protection of the carbonyl group. You will have to look for another protecting group. The second reaction is the addition of Grignard, and we have studied it in case of synthesis of alcohols, where we said that if you have an aldehyde like formaldehyde and then you add a Grignard reagent to your aldehyde, you will have an attack from the Grignard. Introducing the R that was attached to your organometallic compound, and then the oxygen will abstract a proton from the medium, giving a primary alcohol. Since your aldehydic group was attached to two hydrogens, so it will keep the two hydrogens and only one R will be introduced from your Grignard. However, if you use any other aldehyde, you already have an R attached to the carbonyl, and using your Grignard, you will add another R. So now your carbonyl will be attached to two carbons and the OH, so this is secondary alcohol. Finally, if you start with a ketone, then your carbonyl is already attached to two carbons, and you will introduce the third carbon from the Grignard reagent, and accordingly you will end up with the tertiary carbons. So primary alcohols can be produced from addition of Grignard to formaldehyde only. Secondary alcohols can be produced from reaction of Grignard with any aldehyde other than the formaldehyde. Finally, the tertiary alcohols will be prepared from the addition of Grignard to any ketonic compound. The third example of nucleophilic addition reactions is the reaction of the carbonyl compounds with cyano compounds. The cyano group is carrying a fully negative charge, and the carbonyl of the carbon of the carbonyl is carrying a partial positive charge. Accordingly, you will end up with such a compound. It's a carbon carrying an OH and a cyano group at the same time. We call this class of compounds cyanohydrins. These are cyano compounds that have an OH on the same carbon of the on the carbon attached to the cyano group. These are very important class of compounds because you can actually hydrolyze them into the hydroxy acids. The cyano group can be hydrolyzed into carboxylic groups, and it will be carrying a hydroxy group on the alpha carbon to the carboxylic group, so you can actually produce alpha hydroxy acids, or you can reduce them into amines that are carrying an OH beta to the amino group. So this is why cyanohydrins are an important class of compounds. So as we have mentioned, we have 3 examples of reactions that are considered as nucleophilic addition reactions to carbonyl. The first type is the addition of an alcohol molecule giving the hemiacetals and the hemiketals. If we add only one molecule of the alcohol, however, these are not stable, and this is a reversible reaction that goes back to the carbonyl compound. However, a more stable form is the full acetal and the full ketal, where we add 2 alcohol molecules to the aldehydic or ketonic compound. To identify an acetal or a ketal, you will have to see a carbon attached to 2 O alkyl groups. To identify a hemiacetal or a hemiketal, you have to identify a carbon that is attached to an O alkyl group and an OH. As we've mentioned, we have a very important example of these acetals, which are the cyclic acetals and the cyclic ketals, where we use ethylene glycol as a dihydric alcohol that represents, it's as if we are actually using 2 alcohol molecules, but we're actually using 1 because it has 2 OHs. It produces the cyclic acetals and the cyclic ketals, and these are very stable and they can be used to protect carbonyl compounds during reactions. As we mentioned, if you need to perform a reaction on a function group in the side chain of your carbonyl compound and you fear for the carbonyl to react, you can perform the reaction of the formation of the cyclic ketals and acetals through addition of ethylene glycol, and then you perform your reaction on the side chain and then you hydrolyze your ketal or acetal. But as we have mentioned, you have to be very careful that the reaction conditions that you are running on the side chain does not involve any acidic conditions, because acetals and ketals are easily hydrolyzable in acid medium. The second reaction is the organometallic compounds, and as we have mentioned, the formaldehyde gives a primary alcohol. Any other aldehyde gives a secondary alcohol. And finally, ketones give a tertiary alcohol. The last reaction was the addition of hydrogen cyanide, which is a reaction that forms cyanohydrins. What are cyanohydrins? These are compounds that have a carbon attached to an OH and a cyano group at the same time. These are very important class of compounds because they can be easily hydrolyzed into the acid and reduced into the amines, giving either alpha hydroxy acids or beta hydroxy amines. Now, the second type of reactions that we will deal with during this video are the condensation reactions. What are condensation reactions? As we have mentioned, you have a carbonyl compound, you have a nucleophile that is carrying a hydrogen. The nucleophile will attack your carbonyl, breaking the double bond, and now the nucleophile is attached to the carbonyl and it's still carrying a proton. Accordingly, a condensation step will take place, producing a double bond between the nucleophile and the carbon. A very important example for such reactions are amines, whether they are primary or secondary or amine derivatives. If you perform this reaction, you have the amine that will attack your carbon, and now the amine has a proton attached to the nitrogen. This proton will be removed with the OH on the carbon, giving the imine. This is if your amine is a primary amine. However, if your amine is a secondary amine, so if your amine is a secondary amine, you will have the nitrogen attached to 2 R's and then a hydrogen. So when it reacts with the carbonyl, it will have no more hydrogens attached to it. It will have 2 carbons, so it cannot continue the condensation. It has one of 2 choices. It either stops at this step of the hydroxy amino compound, or if your carbonyl compound was carrying an alpha acidic hydrogen, this hydrogen will leave as a molecule of water with the OH on the carbon, giving this structure. So it's like the carbonyl was looking for, after it became an OH compound, was looking for a proton on the nucleophile. It did not find the proton on the nucleophile, so it looks on the other side, which is the remaining of the aldehyde or the ketonic molecule. If it finds a proton, it will condense with it. It will lose the molecule of water again. These compounds, we call them ene, from the double bond, ene, and then you have amines. So these are ene amines. Okay, so this is the 2 types of condensation. It's either a primary amine and you perform the full condensation with the amino group, or it's a secondary amine where you run the first attack by the amine and then the condensation will proceed using the hydrogen that is present alpha to the carbonyl of your starting material. As we've mentioned, not only primary and secondary amines, we have the amine derivatives. If you have amine derivatives, these are compounds that have the amino group, but instead of an R, you have different substituents. These substituents can be an OH, or another amino group, or the third is a substituted amino group. If you have the OH, your product is an oxime, and we will discuss it in full detail. If you have another amino group, then your product is a hydrazone. Let's discuss these in full details. So, in case of hydrazones, you have the carbonyl compound and you reacted with the derivative of the amine, which is the hydrazine. What happens here is, first you have the N attacking the carbonyl, giving this compound, which will lose a molecule of water to give the hydrazone. This is a very important reaction because if you add sodium hydroxide with this hydrazone, you will reduce this compound into the alkane. Remember, this reaction was called Wolff-Kishner reaction, where you used to react a carbonyl compound with hydrazine in presence of sodium hydroxide, and your end product was an alkane, where you removed the oxygen and you added 2 hydrogens in its place. So these are the hydrazones. The second reaction is the oximes, where you react the carbonyl compound with hydroxyamines. The product is, again, you will have the same attack. You will have the OH, and you will have the nitrogen carrying an OH and an H. Again, the condensation proceeds and you lose a molecule of water to give a C doubly bonded to an N, which is carrying an OH. This is a very important class of compounds because they have some sort of geometrical isomers. How is that? You have a double bond. And as we have mentioned in stereochemistry, please refer to the stereochemistry videos. We said that if you have a double bond, then you have restricted rotation. Groups that are attached to the different 2 atoms that are forming the double bond are not interconvertible. They cannot rotate around the double bond. So if you have an R, say we have a methyl and a phenyl, and you have the OH. You have 2 isomers for this compound. What are these two isomers? You have now the carbon doubly bonded to the nitrogen, you have the methyl group, and you have the phenyl. It depends on whether your OH is on the same side of the double bond. Here is your double bond. If the phenyl is on the same side with the OH, then this is the syn phenyl, and then you mention the other group, which is the methyl ketoxene. However, if you have the other derivative, which is you have the OH and then you have the methyl at the same side, this is your double bond, and now you have the methyl and the hydroxy group on the same side, then this is the syn methyl. And then you mention the other group, which is the phenyl and ketoxene. By the way, we can name both of these compounds in a different way. Here you have the methyl on an opposite side of the hydroxy, so you can say that this is the anti-methyl phenyl ketoxene. And the same way you have here the phenyl on an opposite side to the hydroxy group, so this is the anti-phenyl, and then you mention the other group, which is the methyl ketoxene. This is in case of ketones. However, so this is how your compound was. You had the ketonic compound and you had your oxime. Sorry, you had your hydroxylamine. They reacted together, you removed this O with these two hydrogens and you produced this compound. How about if you started with an aldehydic compound? You will have an R and an H attached to your carbonyl, and then you reacted with your hydroxylamine. Again, you remove the molecule of water and you have the double bond between the nitrogen and the oxygen. Now all what you need to look for is the hydrogen. Where is the hydrogen relative to the hydroxyl group? If you have this isomer where the hydroxyl group and the hydrogen are on the same side of the double bond, this is your syn-aldoxene, which is much easier than ketoxenes because in case of ketoxenes you're looking at two different groups. However, in case of aldoxenes, you are only looking for the hydrogen versus the hydroxy group. If they are on the same side, then this is the syn compound. If they are on opposite sides of the double bond, this is your double bond, you have the OH on opposite sides to the H, then this is the anti-aldoxene. These compounds can be easily differentiated from each other using a very famous reaction which is called the Beckmann rearrangement reaction. What is the Beckmann rearrangement reaction? It's a reaction where you actually react an oxime. Say we use this isomer. As we have mentioned, you have here the phenyl on the same side of the double bond as the OH. So this is the syn-phenyl methyl ketoxime, or you can name it according to the group which is in the anti position. So this is the anti-methyl and then phenyl ketoxime. In Beckmann rearrangement, all what you do is that you add conc sulfuric acid to your compound. It's a proton. You're just adding a proton to produce protonation of this OH, removing a molecule of water and putting a positive charge on the nitrogen. To stabilize the positive charge, an alkyde shift takes place. But which alkyl group? Is it the methyl group or the phenyl group that will migrate to the nitrogen to neutralize the positive charge. It's usually the group that was in the anti-position to the OH, because this reaction takes place simultaneously. What happens is that the OH, the molecule water, does not leave first and then the methyl moves to the nitrogen. They actually take place together at the same time. So they cannot take place if they're both from the same direction. They will collide with each other. It's much easier if the group in the anti-position moves and migrates at the same time the water molecule is leaving. So the group at the anti-position is the group that moves to the nitrogen. And now the carbon of the carbonyl or the oxime is carrying a positive charge. Your medium still contains water molecules that has an oxygen carrying a lone pair of electrons. So now your carbon is carrying an OH group. A hydrogen leaves to neutralize this positive charge. And what you have now is what we call an enol form. What is an enol form? A double bond attached to an atom which is carrying an OH. This is the en and this is the ol. And as we all know, enol forms are unstable. They perform an equilibrium to give the ketonic compound. So what you actually end up with is an amide. Okay, so this is Beckmann rearrangement. How can we use Beckmann rearrangement to differentiate between different isomers? If you have this oxime, this is one isomer where the methyl was the group that was in the anti-position to the OH. So this means that you will end up with the methyl attached to the amino group of the amide. And the phenyl will stay on the carbon. However, if you have the other isomer where you had the phenyl anti to the OH, the phenyl is the group that will actually migrate to the carbon, to the nitrogen, and the methyl will stay on the carbon. If you hydrolyze this compound, it will give you benzoic acid and methylamine. And if you hydrolyze this compound, it will give you acetic acid and aniline. If you revise how you can identify different acids, you will remember that a very simple test, which is neutral ferric chloride, will differentiate between benzoic and acetic acid, where benzoic acid will give a buff precipitated while acetic acid will give a red color solution. Again, the aniline can be identified from the methylamine. So Beckmann rearrangement is a reaction that can be used to differentiate between the different isomers. We can identify which isomer we have using the Beckmann. You just take a drop of your oxime and you add a drop of conch sulfuric to it. And then you allow the reaction to take place and then you hydrolyze. And then you test for the acid or for the amine that can be produced by this reaction. You know that you can have one of two acids depending on the groups you had. You had a methyl here and the phenyl here, so you can end up with benzoic or acetic acid. These are the two acids that you can actually end up with. So you can test for them. Suppose you have different acids, you will have, suppose you have different groups on the oxime, then you will have different acids. And you can know the positions of the alkyl groups relative to the OH using Beckmann rearrangement. Beckmann, or not Beckmann itself, a modification of Beckmann has been used to identify again the different isomers of the ald oximes. As you have seen, this reaction deals with the ket oximes, where you have two groups where you have two R's attached to the nitrogen, and you are trying to decide which one is in the anti position and which one is in the syn addition to the OH. You use Beckmann rearrangement. Now, if you have an aldoxime, this is the syn aldoxime, and you have the anti-aldoxime. Again, if you add a drop of inorganic acid, something like sulfuric acid, for example, you will protonate the OH of the oxime. If you have a hydrogen, if you have an R in the anti position, as we said, the group in the anti position is the one that actually reacts. So an R will not easily migrate if you have a hydrogen attached to the carbon. So this reaction will not proceed and it will give a negative reaction. However, if you have the H in the anti position, the reaction will proceed, giving the nitrile compounds or the cyano compounds. So only the anti-aldoximes will react by this modified Beckmann rearrangement, giving the cyano compounds. However, the syn compounds have the OH in a syn position to the has the H in a syn position to the OH, and accordingly it cannot migrate, it cannot react, and accordingly this will give a negative reaction. So as we have mentioned, the condensation reactions are mainly relying on the presence of an amino group, whether primary or secondary or amine derivatives. If we start with the primary amines, we say that they form the imines through first formation of a hydroxy amino compound through the attack of the amino group. Remember, the amino is a weak nucleophile, so your mechanism should go through the weak nucleophile mechanism by introduction of an inorganic acid. And then the second step is the elimination of the molecule of water, giving the imine, or what we call Schiff's base. These are very important compounds because they can be reduced into different substituted amines. The second reaction was the addition of amine derivatives. As we have said, you remove the R and you add a different substituent to the amino group, giving your different derivatives. As we have said, if the Y is an OH, you end up with an oxime. So this is the hydroxylamine. If the Y is an amino group, this is the hydrazine, giving the hydrazone. And if it's an amino phenyl group, this is the phenylhydrazine that gives the phenylhydrazones. Looking at the hydrazones, we said that they are very important intermediates in the Wolff-Kishner reaction, where you react the carbonyl compound with hydrazine in presence of sodium hydroxide. First, the hydrazone is formed, which is not isolated, and then you reduce to the alkane. Then we discussed the oximes, whether ketoximes or aldoximes, depending on your starting material. If you start with an aldehyde, then these are the aldoximes, where you have one of the groups attached to the carbon as a hydrogen. And if you start with a ketonic compound, you will end up with a ketoxime, where both R's are carbon atoms. As we've said, these are geometrically isomeric compounds. They have geometrical isomerism due to the arrangement of the groups around the double bond. We specify where the double bond is first, and then we look at the different substituents relative to the OH. As we have mentioned here the phenyl is on the same side with the OH, then this is the syn phenyl. And the methyl is at an opposite side of the OH, then this is the anti-methyl. You can name it according to the syn group or to the anti group. And the same applies here. In case of aldoximes, we said that you only look at the hydrogen relative to the hydroxyl group, where they are from the double bond. If they are on the same side, then this is the syn aldoxime, and the name of the oxime will depend on the R group. So this is the syn-benz aldoxime. And if they are on opposite side of the double bond, then this is the anti-benz aldoxime. As we've said, we have a very important reaction that differentiates between the different isomers, which is the Beckmann rearrangement, where you add consulfuric to your oxime. What happens is that the hydroxyl group goes away. The group that was in the anti position migrates to the nitrogen, and the carbon converts into a carbonyl compound, giving an amide compound. The mechanism, as we've mentioned, first proceeds through protonation of the hydroxyl group, removing a molecule of water, putting a positive charge on the nitrogen, and quickly the group that is in the anti-position, that was in the anti-position to the hydroxyl group, migrates to the nitrogen to neutralize the positive charge, leaving a positive charge on the carbon. And then the molecule of water that has just left attacks the carbon that is carrying the positive charge, putting an OH on this carbon. Now this is the enol compound, which is unstable, and it is always existing in an equilibrium form with the keto form. The keto form is the more present form. By the way, I need to mention here, if you have any carbonyl compound, say acetone, up to 99% of the acetone is in this form. However, you have a very small amount of the acetone in the enol form. There is always a tautomerism between the enol and the keto form of any carbonyl compound. It's true that the keto form is the more stable and it's the more present, it's the more available form of the compound. However, it doesn't mean that the enol form does not exist. We said that you have a very similar reaction, or you can use the same principle to differentiate between the aldoxenes, where you add a consulfuric acid to your aldoxene. If the hydrogen is in the same position, this reaction will not proceed, while if the hydrogen is in the anti-position, the reaction will proceed, giving the nitrile or the cyano compound. As we've mentioned, these reactions can be used, the Beckmann rearrangement can be used to differentiate between the different isomers of ketoxenes. As you see, these two compounds are almost the same. The only difference is that in the geometrical isomerism around the double bond of the ketoxene, here you have the phenyl anti to the OH, and here you have the methyl anti to the OH. So here the methyl is what will migrate to the nitrogen, and here the phenyl is what will migrate to the nitrogen. So this ends up with the methyl N-methyl benzamide, and this ends up into the N-phenyl acetamide. If you hydrolyze both, one will give the benzoic acid and methylamine, the other will give the acetic acid and aniline, and these two different acids can be tested for using neutral ferric chloride. So this way you can actually differentiate between the different isomers of your ketoxene. Finally, we said that the third type of reactions is the secondary amine, and these can give the ene-amine if the alpha carbon to the carbonyl is carrying a hydrogen. So the carbonyl will first look for the hydrogen on the amine. It will not find a hydrogen to condense with. It will look on the other side. It will find the hydrogen and it will form the ene-amine. This way we have finished the second part of aldehydes and ketones, where we have discussed the first two types of reactions: the addition, nucleophilic addition reactions, and the condensation reactions that involve first nucleophilic addition and then a loss of molecule of water. Next video will deal with the second two types of reactions, which are the reactions of the alpha acetic hydrogen and the oxidation reduction reactions.